So in my last video, I did mention that while the calculator gives really good estimates of definite integrals, it doesn't catch all of the issues we could have when calculating a definite integral. Uh, and specifically, it has problems with discontinuities. Um, Now, the really nice thing is with this kind of backwards from derivatives. With derivatives, if I have a discontinuity, I can't find a derivative at all. So we had to be very, very mindful of discontinuities because those are places the derivative can't exist automatically. But most discontinuities are not an issue for definite integrals because most discontinuities are infinitesimally small. They actually, like the one rectangle that would be affected by them is so tiny that it doesn't have an impact on the rest of the rectangle's areas. The one exception is a vertical asymptote because the heights of rectangles are approaching an infinite height. So their areas are becoming infinite. And this is where it gets a bit confusing. At the AB level, you would just say, oh, vertical asymptote, we're not going to have any possibility of evaluating this definite integral. It doesn't exist. But at the BC level, we have to actually study this because sometimes we can evaluate a definite integral with a vertical asymptote within it. Sometimes we can't. That's actually its own kind of mini unit that we have to study near the end of the course in BC. But holes, move points, jumps, they're so tiny, it's not a problem. So some examples of this would be if I handle the hole or a move point or a jump example first. So the blue, if I say I want the integral from 0 to 4, and I'm going to say that this is g of x with respect to x, it says I'm going from 0 to 4. And that means I can do it as an area between the function and the x-axis. Well, what that really is I have two rectangles. One rectangle, and they're both above the x-axis, so the definite integral will be exactly the same, is a 1/2, and the other is a 3/2. And so I could evaluate that, and the discontinuity had no impact. But then, if I were to look at the top example here and said, and this is f of x, said I want the integral from 0 to 4 of f of x with respect to x. Well, that means I'm finding the area, but now as I'm getting closer and closer to the 0, it keeps going up. I never actually have a top to my rectangles. So this does not exist because I have a vertical asymptote at x equals 0, which is within my bounds. Now, if I'd said I want to know the definite integral from 1 to 4, it's not being affected by my discontinuity or by my vertical asymptote, so that would be okay. But as soon as the vertical asymptote is in between, I've got problems.